everybody. Welcome to the Satellite Techno-Archeology Old Data Answers New Questions Earthdata webinar. This is your host, Jennifer Brennan. I'd like to thank all of you who have stuck around for the rescheduled webinar, and sorry that we had to cancel it at the last minute on the 27th. So while everybody's logging in here, we do have the two optional polls at the bottom left and middle of the page, and I appreciate your feedback on these. I've got 3 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started here. First, what I'd like to do is touch upon a few housekeeping items related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod located on the lower right-hand side of your screen. And again, this works like a chat. This webinar is being recorded and will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earthdata YouTube channel within a few days of completion. The URL will be provided to all of you at the end. All presentation files will also be available for download at the end of the webinar. We are going to take 1 hour for this webinar. 45 minutes are allocated to the presentation with an additional 15 minutes for the question and answer period. After our speaker has finished his presentation today, what we'll then do is we'll move to a final set of polling questions, and from there we will transition directly to the Q&A period. Remember, you do have an opportunity to ask questions throughout all portions of the webinar by using the Q&A pod. Questions will not be answered using the raising hand function. It has been disabled. One final note, depending on the volume of questions that are received, we will extend the Q&A period an additional 15 minutes to 4:15 p.m. for those of you who may wish to stay on the line. What I'd like to do now is move to our agenda for today. Okay, during today's webinar, our speaker will start off by introducing the data rescue efforts and the rationale behind these efforts. Next, he will describe the painstaking process that was implemented to complete the data rescue project. Finally, he will present several old satellite data images from the 1960s and 1970s and speak to the gain from this project undertaking. With that, it is my pleasure to introduce today's speaker, David Gallagher, who is a Senior Associate Scientist and Manager within Information Technology Services at the National Snow and Ice Data Center Distributed Active Archive Center, or NSIDC DAC. David?
Thanks, Jennifer. Hope you can hear me. And I'm hoping I'm going to see a slide here right quick. Excellent. I do see a slide. So I'm here with Garrett Campbell, and we're going to give you a little background on the project, how it worked, and basically as Jennifer described. So I just want to step through the agenda of the thing here and give you at least one little image. The image you're seeing over on the right side of the screen is a high-resolution infrared false color image. This is 1966. And if you look over to the right side of the image, you'll see a couple of typhoons. The big green splotch in the middle is the Himalayas, and that's the coast of China. So why do this kind of effort? It's a lot of work. It's not easy to do, so let's just jump right in. Why do you want to do this? Because of change. In no uncertain terms, it's change that drives it. If you don't know what came before, you can't tell what's changed. If you look on the left there, you'll see the aerial C, and I want to point this thing out. I call it the dog head right here. See if I can get this thing to come up. Right here is this little feature right here. Looks like a head of a dog. Here's the same feature 50 years later. And you can see the entire aerial C is now gone. We have imagery going a long way back. Looking over here, this is Greenland in 1962, and fairly amazing satellite-based data from that far back. So why do this? People say, well, the data, it's old, it's not any good, they didn't have the technology then. Well, honest to Pete, we don't have a time machine. It'd be lovely to be able to go back in time and get this stuff, but that's not an option for us. So the historic data creates that baseline that you can then compare to. It gives you an idea of what the extremes were. And let's face it, the taxpayers put up a lot of money to put these satellites up back at the time. It's great and of high value that we can still get new science out of this old data 50 years on. A lot of data has already been lost. The Defense Meteorological Space Program, all the data from prior to 1973, and they collected it all the way back to 62, virtually all of it's gone. It was tossed. It was considered like yesterday's news, and they didn't need it. For those of you who have digital tapes and say, well, those tapes are so old, nobody can read that stuff, we should just toss those tapes, please don't. There is now technology where any tape, any format can be read. It's not dirt cheap. I think it's right now, I think NASA's paying about $35 or $40 a tape, but it's pretty reasonable to recover that old data. So this is by no means the only data rescue project. I just want to point out a few. The Lunar Orbiter Project, 1966. This is they have been recovering 40 centimeter data off the lunar surface from prior to the landings. The British naval data in the 1700s. It's been amazing. They actually went to huge lengths to record salinity, barometric pressures, and temperatures throughout the world in the 1700s. So they've been making that a crowdsourced project where people are getting 2 pages of a captain's ship log and then trying to enter that data into some sort of a coherent database. Mariner 9, another great NASA mission, that data is now trying to be recovered. But anyway, you can see from the list here, there's a lot of amazing projects, and this is, again, by no means a complete list. So the pain of doing the data rescue is, when it comes right down to it, you're converting from whatever you got into some sort of digital form. The media, it could be film, it could be paper records, could be mag tapes, could be scribbled notes, could be whatever the heck. And the question you have to ask is really, how dark is your data? And by dark data, I mean data that you can't go in and say, I need to select this. I want to get it by this time, this place, this event, these readings. You can't, the data is dark. It's simply, there's no way to get it. For us, when we called up the NCDC, this is the National Climate Data Center, and asked for the NIMBUS data, they laughed and said, we said we'd like Greenland and Antarctica, and they laughed and said, you can't get that. Well, you've got the data. The records here say you have it. Yeah, we've got it. It's in boxes, and it's recorded by orbit number, and there is no way for us to get it to. If you want that data, you're going to have to take all of it, and that was a bit daunting. So what's the state of the data? Is it falling apart? Is it in a major risk of coming apart? Is there any data about the data, the metadata? Can you find that thing? Is it possible to pull this back together? Obviously, funding is a major issue. What are you doing this for? And is the purpose you're trying to do it for, is it possible to do what you're doing? And lastly, make sure you actually have an actual science question that you're trying to answer with this thing. Collecting the data or recovering the data for the data's sake is probably not a viable option. So here's a few questions we should have asked that we had to answer ultimately. Is who are the other users? Just how large is this thing? How good is the data in terms of not only is it its quality, but how intact is it? What are the problems? Was that sensor operating the same way all the time? Was it consistent? Are there parts missing? Who took out parts of it and never returned it? How many steps are you going to have to go through to get this thing to work? Is there something you compare this to? And again, funding is a huge issue. And the last one, which is we found to be very true, is trying to find anybody alive who still knows anything about the data. The guys who'd worked on this stuff back in the 60s are obviously all in their 80s now, and that became a challenge in its own right. I had one guy who was a lead researcher in the 70s, and he would only talk to me if I said I was a member of a credit union, because he was head of the NASA credit union. He'd gone on, and would only speak if you were a proper credit union member. So after saying yes to that question, he finally was able to tell me some information. So let's get into the specifics of this data project. So this project really started after John Moses of NASA Goddard had collected a bunch of the high-resolution infrared data and was showing that they had recovered some of the stuff. And the first thing to look at was to say, gee, it looks like we might be able to see ice edges in that data. Is that possible? So with that, we started a project to try and say, could we find the polar ice extents, both over both poles, the Antarctic and the Antarctic, in the period of the 1960s through the mid-70s? The data was very dark. It was either on this, at that point on tape in forms that had not been used in years, or it was on film, neither of which was going to make it easy to use. But the idea was to push back the historic climate records by 16 years if we could pull this off. So there you can see when these various NIMBUS flights went up. NIMBUS 1 only lasted a month, but by almost sheer chance, a lot of the times that these things were recorded, it happened to catch the sea ice minimum or maximum during the time of its flight. So the NIMBUS sensors had 4 sensors on it. There was one more that was something called an ATP, which is an automatic transmission program. And that's something that actually transmitted down so the guys on basically teletype machines or thermal paper output could actually see the data. It was very low quality and it was used for weather forecasting, but these were these other 4 sensors, the high resolution infrared, medium resolution, the advanced VidCon camera system, and the image detector systems were the devices. Now you notice these are only 4-bit image on the AVCS. So the data was stored on these old tapes, and the film was stored on these 100-foot film rolls. So the objective was to simply say, could we get these ice extents? Oddly enough, and no one really knew, especially they had a pretty solid idea over the Arctic, but over the Antarctic, nobody really knew where the ice extent was. NASA took a stab at it back in the early 60s and came up with some numbers by basically laying the pictures in the floor of a gymnasium and trying to determine the ice edge. But they had nothing to compare it with since no one had ever done that determination. Were they right? Were they wrong? Is this a lot? Is it a little? They just didn't know. The data was considered so vast in the documentation, we got a kick out of this, that they said no one will be able to look at it all. It was 56 gigs. But this is important to realize that in that time, that was more disk space than existed on the planet. So this was a huge amount of data. The machines of that era simply couldn't process that much data. I mean, when your phone is probably 10 times better machine than the computers of the era. So could we process this data? Could we get an ice extent, and could we extend the record? That was our objective. Now, this comes up a lot, and people say, well, you're now trying to build this model. You're going to try and use it to do forecasting on the climate by going back further in time. And people say, well, you can't predict the weather. How can you predict the climate? Well, this is an analogy that I rather like. The weather forecast is basically looking at one tree. Let's say this tree is in Vermont, and you're trying to say when one particular leaf on that tree is going to fall off. This is akin to the weather forecast along the Front Range of Denver. And so you're looking at that one leaf and saying, is it going to fall off the next hour? Is it going to fall off the next 2 days, next month? Difficult to predict. It could fall off any time. Climate forecasting is predicting when all the leaves on the tree are going to fall off. So when it gets to be late September, yeah, these are all going to fall off the tree. As climate changes, that date may shift. So the historic data basically improves both forecasts. So let's jump onto the recovery of the NIMBUS tapes. Goddard Space Flight did an amazing job working with a company called JBI up in Montreal, who built a machine that could read these tapes. So they recovered 4,000 of these tapes. And these were in tape archive program format. The tapes were in such bad shape that the iron ferrite was literally falling off the acetate, the film layer. So the solution they found was to bake the tapes in an oven at 175 degrees, or until the tapes rose and until the tapes were basically until the iron ferrite and the acetate got sticky enough that they would hold to each other. Keeping the temperature below that was critical because otherwise you could alter the bits on the tape and in essence erase the tapes. So the tapes were then read processed, and they recovered 99% of this data. It was a pretty amazing feat. One of the problems that cropped up was that in an effort to save storage on the tapes, and tapes were very expensive at that time, the record you see up here at the top, let me show you what I'm pointing to, right over here, this was the entire record that was recorded by the spacecraft. And so they had sync pulses, they had the actual data recorded, they had a calibration strip, and all the rest. In an effort to save space, they trimmed this off. And the problem came in where they tried to trim it at the edge of space when the spacecraft would have been seeing the horizon. So they clipped that off, but they didn't necessarily do it the same way every time, and that resulted in what you see here. The shore of Lake Michigan looks kind of choppy. So we had to write software to clean that up, and this is the result. And this was a fairly major effort, but this resulted in a much cleaner data set. And again, this is the kind of thing you can run into with data rescue. So here you can see some of the processed imagery. So if you look right over here, you can see what looks to be an ice edge right there. And we can see what looks to be an ice edge over here. There's a lot of noise in this data that would have to be cleaned up. That's part of the Antarctic Peninsula right there. But it's tantalizing that there might be something there. And this is looking at this is, again, the high-resolution infrared from 1969. So in order to do this, we had to align the scan lines. There's rectification, regridding, merging into time composites by a certain span of time, something in the order of a week, and then try to determine an ice edge from that. So that was the effort we were undergoing. Here's some of the idea of what we got. The problem was we found that we could find the ice edge sometimes, but we couldn't find it consistently, and we couldn't tell when we were really finding the ice edge and when we weren't. This was because the ice and the seawater were oftentimes the same temperature, or sometimes the ice was warmer than the water, and other times the water was warmer than the ice, depending on the conditions. So we were kind of stuck. We did find, however, that this data has lots of other potential uses. For example, sea surface temperature is possible. They wrote algorithms back in the 70s, and those algorithms, I think, could be recovered to come up with a way to calibrate this data to get. But if you look right over here, you can see this is the Gulf Stream and the edge of the Gulf Stream. And right over here, you can see whatnots that I think it would be pretty easy to go through and determine the La Nina and El Nino years looking at the sea surface temperature. You can actually see it's a little brighter in here. So there were other sensors on NIMBUS. We said, okay, what else can we do? There was the film data. This was the AVCS and IDCS. It was recorded on film and had been sitting in Suitland, Maryland for about 25 years, and then it was picked up, and the place it was stored in Suitland was not a temperature-controlled facility. It was basically just a warehouse. It was picked up out of the warehouse and moved to NOAA's Climate Data Center. They kind of agreed to take it, and it's an enormous facility they have down there, not as big as what you see here with the Rays of the Lost Ark, but nonetheless quite large. We asked how many times anybody had requested and gotten the data, and they said none. They said, you've had the data for 25 years and no one's ever requested it? I said, oh no, we've had lots of people request it, just nobody could ever wanted to actually take on trying to use it because it was going to be too big a task. When they realized they have to recover all of it to even get a single image, because we can't tell them where anything is on this film. So we now had the data. Could we do anything with it? Now, you go, why on earth would NASA have digital data from the spacecraft that they would now play back onto a TV screen, then take a picture of the TV screen? It's because of the sheer size of this thing. It was so big that that was the only economic way they could come up to deal with the volume. To put this all on tape would have taken probably something in the order of 10,000 tapes. That was just too large. So to make an archival copy, this is how they did it. So now we had to come up with a way of, okay, how do we get the data off the film? How do we rectify it? How do we geo-rectify it? How do we pull this stuff? How do we get the metadata? and is this going to work any better? One of the problems with visible light data is clouds, obviously. So how are we going to get rid of the clouds? So the first thing was scan 250,000 images. In order to do that, because the way the camera system worked, it appears that they took a picture and then they turned a crank. And depending on what the operator did, if you turned the crank a lot or you turned a little, because the images were never in a fixed position. They obviously didn't have a system to turn the camera forward. We needed to be able to mark the data. We needed to georectify the whole thing. Fortunately, NORAD still had the ephemeris, the orbital data. So if we knew the time and we knew where the spacecraft was in its orbit at that time, we could say where the camera was looking. And so we were able to merge that into a time composite. However, this meant we had to record the time on every image, even if the image didn't have the time still visible. We had to know where the center of every image was, and none of this could be automated, unfortunately. So we had student labor who had to sit there and look at every image. So the quality of the location also went up quite a bit by going this technique. The best you could get from the image is about a degree or so of accuracy. So we got it down to about 20 kilometers. So here's one of our students, and in doing this exercise, we were concerned for their sanity. Garrett wrote gaming software, is the best way I can describe it, to make this a little more interesting, and it did some prediction to let them know how they were doing, and they could then see the results as they process the data. So they would go through, find one time that they could read, and the system would then try to predict the rest of the times, and then they could go check the location that the system then predicted and said, okay, if you're looking at this image in this location, you should see what? So here you can see right over here, these are the clipped bottom. We clipped off in the digits the times and the metadata off every film piece. And you can see some of them, there's nothing much there to read. Some of them are fairly clear. And this was what the system then tried to predict the time of that event was. And so as the students entered the data, there were 3 cameras, or 3 images taken per scene, one looking straight down, one looking left, one looking right. And so this is part of one orbit right here. So, and again, here's the bottom of one of these images, and here is an image. This is the approximate lat long of the center of the image as recorded by the spacecraft at the time. So this was a fairly complex process. It took us about 2.5 years to get through this effort. So here's an idea of what some of those sample images look like. This was NIMBUS 1's first image, and here you can see broken sea ice off the coast of Greenland. And this is not just any image, it's the first image ever transmitted from space of the poles. Up till this point, data was routinely being, nothing had flown at this high a latitude, and most of the technology of the era was still using film canisters that were being dropped off from space. So this was, again, one of the earliest, highest latitude photographs. Here's an image looking at Baffin Island. Here's an ice cap right there. And you can see some of the issues, though, of, well, how do I know that's ice, and why isn't that ice? How do I distinguish clouds from ice? And this was going to be a problem that kind of plagued us through the project. So here's an image, and this is where Garrett had gone through by hand and had found an ice edge that he looked at visually, and he looked at all 250,000 images. Sometimes it was pretty easy to see. Here you can see ice pack data. Here you can see, looks like an ice edge right over here. Garrett's correcting me. He's telling me it was just the polar images he looked at, so it wasn't quite alternative. We were able to reject the ones that weren't in the poles. But here you can see snow-capped areas of Greenland. So one of the things that really came up that was interesting, some of the NIMBUS data was available, and that was these APT images. You can see this is one of the APT images, and this shows you what And this was the automatic picture transmission, and this came down on thermal paper. So this would have been stuff that NOAA probably would have shown us to give people an idea from space of what Hurricane Camille, which by the way was the most dangerous hurricane to ever hit the United States. It was the lowest low, the most powerful winds. And here's the recovered data to give you an idea of what the difference was. And you can see there's a lot more detail, a lot more quality of the image, and you can actually blow this image up quite a bit compared to what you could do over here. Now, okay, so now we've recovered the data. What is the change? So this is looking at the Independence Glacier in northern Greenland. And I want to draw your eye to this thing. So right from here, from the edge of the ice sheet to the open ocean right here, this is about 70 kilometers. And look back here at, this is NIMBUS 1, September 64. And you can see the ice is going all the way from the ice shelf, or ice sheet that is, all the way down. The glacier is going all the way to the sea. And look at the channels here, and they're all the way filled up. You can see that that ice is now retreated almost all the way back to the ice sheet. This channel right here is now completely open, and at that time it was completely closed. However, look over here. We call this little feature right over here the rhino head. And you can see this little indent right there. You can see that indent is opened up just a little bit more right here. But otherwise, this ice cap has had extremely little change in this part of the world. Keep in mind this is northern Greenland. But it's with this kind of information you can actually now get a rate of change and how fast things are actually going. And again, without this kind of data, there's no way to figure that out. Some unusual features. This was a major whole Polynya open water that we didn't expect to see. And that's an awful lot of what this project found is things we weren't expecting. Our idea is that we would see it was colder in the 60s, we should see more ice, and it should be pretty consistent. And that wasn't necessarily the case. So here we've got what very much appears to be open water, maybe extending all the way out over to here. And this is a feature really not seen till 20 years later. Did these type of events coming up? What caused this? Why was that so big? We don't know. So this is where it gets rather interesting. This is NIMBUS 5 that flew the first passive microwave sensor, and NIMBUS 5 had an instrument that was a 19 gigahertz passive microwave, and it didn't see anything in 1973. It saw pretty much normal-looking ice. However, in 1974, it saw this, what appears to be a major hole. And it's known as the Wendell Hole, and it appeared in 1974, 1975, and 1976. The instrument crapped out after that, and there weren't too many, oddly enough, visible light instruments, so we don't know, but it's never been seen since. We think over here, this is about the same area. Looking at the NIMBUS 1, we found this very dark area that looks like some open leads. Would this have looked like this if we'd had the same type instrument? And so one of our tasks now is to say, can we look at visible, infrared, any other source, and try and compare and see what did this thing actually look like at that time. So we're looking at the possibility of doing that type of analysis. So I want to explain to you a little bit of one of the problems we had. So we tried to manually do this, and Garrett and then the students actually got quite good at trying to find the ice edge, but sometimes it's just really hard to tell. You're only dealing with a 4-bit image, which means we only have 16 shades of gray. From jet black to white, you've only got 16, so it's color, the whiteness of the cloud versus the whiteness of the ice is pretty difficult to distinguish. So we said, all right, this is looking at 1 pixel. So imagine you're looking at a single pixel right here through time. So this time represents about 20 days. So we picked 7 days, which are these ones you see in gray, and we said, okay, looking at those 7 days, give us the darkest pixel over that 7 days. If the pixel was black, that meant we were seeing open water. If the pixel was white and stayed white, it was a high probability we're looking at ice. So we ran that analysis to try and figure out if we could determine an ice edge in a semi-automated fashion, because remember, we have nothing else to validate this against. There were no other recordings. There was nothing else out there. So we wanted to say, how do we actually know what we're seeing? So we used the data itself as a validation, just doing a different technique. That led to these kind of things. So here you can see, you're looking at a polar projection. So this is Greenland right here. So this is basically the North Pole. You're seeing a bit of a glint off because of the way the processing works, but that's basically the pole right here. So here is, this is Norway, Siberia, and over here is, this is Alaska right here. So here you can see we've got some open water patches right in this area. This looks like a major lead going right in through here. This is an island off there. But we actually were able to generate a fairly clean-looking image of what the Arctic looked like. In this case, this is June of 1970. Going into the Antarctic, it actually worked a good deal better. Here you can see melting near the edge of the continent. And by golly, we've got what appears to be another large hole. Maybe this is the same type of an event that was causing the Wendell hole in the mid-70s. Was it appearing in 1970? You can see the edge of the ice is rather raggedy looking, and that's actually how we've seen from later imagery. You can see this little bit of melt coming along the edge, and that's all fairly normal. So we were getting some pretty impressive results. So now we're to compare the result we got from looking at this edge to the result we got looking manually to give us a little more confidence in what we were doing. So this is some of the results. Again, looking over here, you can see this is the edge from the automated process doing it over a 7-day window. And these are the results from doing it manually by looking at those ice edges and trying to come up with what did it look like over that window of time. So we generated these products on a weekly and then monthly basis to determine that ice extent. So here it is again now looking at 1966, and we did this. This just gives you a little sample. So you can see the width of the line, there was a lot of variability. Some of this was because this was done over a month, if you're looking at data, because the ice was actually retreating. And so it's not that we couldn't find the edge, there was actually change as we were looking at it. So here's again a 7-day look, and you can see that ice edge through here. You can see we've dropped the lines on top. So this is where we actually got rather surprised. One of the things that came up here is, again, our expectation we were going to see a lot more ice in both poles because the expectation was colder. And until 2014, we did see, it looked like 1964 was the largest sea ice extent ever seen. And you can see that right here. Oddly enough, in 2014, that number got exceeded. Now, why that's happening, that's a topic for somebody else to discuss. But we found that in 1966, we found the lowest sea ice extent. So what you're looking at here is this is the average extent from the modern record from 1979 to, I think this time this is about 2014, and this is one standard deviation. So this data is well outside of the norm. So in 1964, we saw significantly above a standard deviation. 1966, we saw way below. 1969, we're somewhat below. So the end result is we're seeing a lot more variability than what we expected. And that's not bad. It just shows that you honor the data, see what the data is telling you, and then try and draw your conclusions from that. Why do this? Why go through this effort? Well, again, extending that climate record is part of this thing, and the other is for modelers who are trying to predict the future, if you can give them back another 15 years of data and say, try modeling the data backwards in time. If you can do that, maybe you have a much better chance of modeling it forward in time. So we were interested to see, well, just what was the difference between the 2014 ice extent and the 1964 ice extent. And here you can see the 1964 is in yellow, and so there was a lot more ice off on the upper part of the image here. And in the 2014, there's much more ice down here in the southern part. I shouldn't say southern, but the bottom part of the image. Remember, we're looking at the pole. Everything here is north. So, but remarkably, they're fairly consistent. I mean, it's a very small percent difference we're talking about overall. So this is where it really got interesting. Another group completely independent of us down at Garrett, do you remember? No, University of Tasmania was working on another analysis. They had come up with the idea that they could predict the ice edge extent by using spray from the ocean would spray a certain number of bacteria, and they could detect in this case, from the bacteria, a methylsulfonic acid from the cores. And depending on what the amount of acid there was in the core, they could say how far the ice edge was from the core location. So they built this thing. However, one of the challenges, they built this lovely graph, and this goes all the way back, you can see, to 1840. They had no way to validate it. So they said, wait a minute, you've got a way to look at and figure out where the ice edge was in the 60s? We need to talk. So the red dots on here were the NIMBUS maximum extents that we're seeing looking around the entire continent. And this is the green dots are from Zwally with the ESMR data from NIMBUS 5. And you can see we've got a pretty good match going on. We were actually quite happy to see this. We'd love to fill in some more data here and see how well does it really match across the board. Oddly enough, this technique does not work in the Arctic. It only works in the Antarctic. And again, we're not quite sure why, but it does seem to work. So what about the rest of the 60s? We only got, after all, we recovered this NIMBUS data. We got 250,000 images, but that was only about just a few months was all we actually got of the 60s. It was 7, 8 months, 9 months in the 60s. And then a few months, we got quite a bit more of it in the 70s, but it wasn't by any means the whole thing. It would be really great if there was an operational satellite that recovered every day. It turns out there was. It was called ESSA. ESSA was the Environmental Sciences Services Administration, and this was the precursor to NOAA. Nixon didn't like the word environmental, is what the story goes, and so made them drop the word environmental and go to National Oceanic and Atmospheric Administration. So, but ESSA got the authorization to put up a whole series of satellites, ESSA's 1 through 9. The odd number satellites had, oddly enough, the same type of camera that NIMBUS had. This was a spinning system, and I'm actually pleased to say that we actually just got a very small sum, but we got some funding to actually start recovering this data. The ESSA data was a little nicer in that it was, in some regards, that it had been processed, and it was some of the earliest full digital processing and compositing, I think, done at that time on a CDC computer. And most of the processing was done in the 70s, but the imagery was recorded in the 60s. But it was, again, very nice product. They, again, like NASA, recorded the data on film because of the sheer volume. There's other sources of data back in the 60s, and the biggest one are the Soviets, who had all kinds of missions up. The image on your left, this image over here, is from a Soviet meteor. And look how clean that ice edge is that you can see. And this is 1978, and there aren't a whole lot of sources of visible data. This is 1973, and there are virtually no other sources of visible data except the DMSP data at this time. And this data was taken, I think, before the DMSP data was available. What's interesting is this is a film product. They actually were ejecting a film canister from the spacecraft to get this down, which again explains the high quality of the image. Very good resolution. Oddly enough, just 2 days ago, I heard from some of the Russians who said they might be able to help us find this data. So I'm ever hopeful. So this slide kind of explains what we've done. This in black right over here, this is the passive microwave. This is the classic satellite record of sea ice is the data you see in black, and you see it ends right over here. The Navy took the Defense Meteorological Space Program data, DMSP, and processed it and made their own ice extents. And you can see there's some disagreement over the magnitude, but they're generally pretty good agreement. The green over here is the ESMR data, and then we get into the dark ages where there isn't anything. Now, there's a satellite called CSAT that could give us some confirmation here in '78. It lasted a few months, but if we're trying to get back in the '60s, this is where the gap is. And this is where you can see the values here from the NIMBUS satellites and some of the ESMR, the ESMR data in here. But that's where the data kind of ends. So we're hoping to be able to fill this period of time in, would be the objective. Ultimately, then we get a 50-year record is what we're shooting for of how that ice has changed over time. And that's the big picture objective. So what are we trying to do? Right now, we're working with NASA to see if we can recover some of the NIMBUS 5 and 6 data. That was other sensors beyond ESMR that were on that NIMBUS 5 and 6, see if we can't get back these ESSA data. It'd be great to see if we couldn't get a few of these images from DMSP prior to the standard passive microwave record. Find those ice extents and come up with a way to calibrate these as best we can. I mean, we're only going to be able to do the best you can with it, but get as much overlap where we can to get that put together. So, why do this? Again, what's the point? Why are we trying to recover this kind of data? We're really trying to get to the point where we're getting real change detection. Get those trends over time. How much did it change? And what we're finding is not just getting the trend over time, but where were those anomalies? Where did the surprises come in? Where did we not get what we thought we were going to get? It's those unexpected results is what makes this thing really interesting. You can have a great idea of what you're going to see, but let the data tell its own story. And then compare this data to those more modern data sets. For this project, we were able to find some of those extents. And because of this research, we were able to help other researchers with their proxy studies to confirm some of what they were seeing. The NIMBUS data is a global coverage now. It's searchable, it's subsettable. You can actually get online. You can go to ESDIS, you can go to Earthdata, and you can actually pull down these data. You can look at these images, pull them up, and process them for any number of purposes. And there's lots of other purposes that this data could be used for. This is by no means ice was our target. Remember, we couldn't just get just the poles, we had to get it all back. There's huge possibility of looking at cloud studies in the tropics. For example, has the atmosphere is warmed, are we seeing more clouds or less clouds over 50 years? Well, NIMBUS is going to be able to help answer that question. So, the bottom line, why do data rescue? If you can't tell where you've been, how can you tell where you're going? You've got to have that reference point back in time. That was the challenge that NASA had when they first tried to calculate an ice extent over the Antarctic. They had nothing to compare it to. They had no way to know what the change was. And that's what eventually led NASA in the 70s to realize the incredible value of a time series of data. And they've done a fantastic job in staying on that mission now of making sure from that point forward that they did track all this stuff. And now they're going back in time to get the rest of it. So these are some of the products that we've been able to produce out of this project. We have a global coverage, daytime visible light imagery, and this is the AVCS, IDCS imagery. We have global composites. We have a daily nighttime high-resolution infrared swath. We have high-resolution corrected global composites, and we have ice extents. And you can see here some of the things that people could do with this stuff. So atmospheric sea change, sea ice extents, clouds, historic storms, reanalysis, long-term climate modeling are all things that could be done with this data. So if you're interested, I encourage you to go ahead and try and pull some of that data down. So in summary, this was a NASA-funded project, and we've actually gotten several awards for this project. One of them is the first annual Data Rescue Award. We won that. The data is now in modern formats under Worldview Earthdata, and it's also available at NSIDC. Considering the cost of what it took to get this data in the first place, data rescue is a real bargain. Great return on investment, small money spent to get it back, and this was all done under a NASA contract with the University of Colorado. So with that, I thank those of you attending, and if you, I'll turn this back over to Jennifer, and we can get into the question and answer phase.
Okay, thank you, Dave. Thanks, everybody. What we'll do now is we'll move to a final set of polling questions. And just one clarification, the data, I don't believe, Dave, is available through the Worldview application, but rather through the Earthdata search mechanism. Because yes, we've got our, we do have some historic data, but I think Worldview is more your near real-time data products right now. But certainly if anybody has any questions, for example, feel free to email me and I can put you in contact with either of our two, our speaker or the panelist that worked alongside, Garrett, that worked alongside with Dave on this project. All right, so thank you so much. We'll give these just a couple of minutes, and then from there we'll move directly to the question and answer period. All right, thanks, everybody. Okay, everybody, thank you for your responses. At this point, we will move to the Q&A period. And you'll see in the lower right-hand corner of your screen that I have the presentation from today is posted both in a PDF format as well as a PowerPoint format. And so, if you were to left-click on either of those files, you should be prompted to download the presentation. And then I do have on the left-hand side information about how you can, there's a email listserv to sign up to receive announcements for upcoming webinars, as well as to connect with us on our social media channels. So I'm scanning here to see if we have any questions. If you have any questions, again, what you should do is type these into the Q&A pod, and I will read them for our speaker to answer. Any questions from anybody? There's got to be a question. So I have a question. You may have covered this, Dave. What was the time span, the entire duration of time that it took for this project to recover the NIMBUS data?
Let's see. We started the project, I think I saw 2010.
Okay.
Yeah, I think I started the project in 2010 is when I might have seen John Moses' efforts in 2009 at the AGU meeting in the fall of 2009, and then we started kicking around the area. We got a small grant from our parent organization called Ceres to begin studying the problem, and I was working with Walt Meyer on that one, who is now with Goddard, and to try and actually determine if this was even doable.
Okay. Thank you, Dave. So we do have a question, and I'll just read the entire, there's the, it's got some additional information. So you mentioned other possible uses for the data, such as sea surface temperature. Some of those applications would require more accurate calibration than looking at clouds or pictures of ice. Is there anything resembling calibration or pre-launch data recovered? And then the second part is, has anyone tried an application that requires more accurate characterization? And if you need me to repeat that, I can do so.
In the 1970s, they actually did some sea surface temperature analysis where they had created various calibration and correction algorithms to try and get a sea surface temperature from this data. Keep in mind the data has a temporal resolution of about a degree. So modern data is about 1/10 of a degree or better. So, but they did have the techniques to do it then. I think there are research papers out there to recover that. Garrett, you want to add something?
We can see in the visual representation of the infrared data things like the Gulf Stream. So if you use some kind of calibration points like buoys that might have occurred in the image, I think you could get a reasonable estimate of the sea surface temperature.
There were various atmospheric corrections as well that they had at the time. They did have, some of it would be they had a medium resolution infrared that actually had 10 bands. Was it 10 or 7? 7, okay. Anyway, there was some number of bands, and so using that as a kind of a course correction, I think that would be possible, and I think that's the techniques they used at that time. And that's why the medium resolution data is still valuable. It's pretty coarse. It's 50-kilometer resolution as opposed to the HRIR's 7 or 8 kilometer. Yeah. So, did I answer the second question? Does that cover it? No.
Yes, that does answer the question. And so one of our participants has been experiencing some connection problems and wonders whether or not there is somewhere where he or she could retrieve more information or background information on this project. I mean, the one thing that I could do is to put the two of you in contact offline as well. But if there is any information online, either Garrett or Dave, that would be useful.
Yeah, you can go to the NSIDC website, and there's quite a bit of information there, and we've actually, Garrett and I, Walt Meyer, and, I'm thinking of other authors. Anyway, we did put a whole paper together on how this project was actually done, and we actually got into pretty good detail, so that's been published as well. John Moses and Dennis Wingo are the other authors.
So I think what I'll do, I've included the website, the nsidc.org website here, but I think I'll put the two of you in contact via email offline, if that's acceptable to our participant. Are there any additional questions at this time? Anybody?
All quiet on the Western Front. Okay.
Well, just a reminder, within a couple of days of completion, I should have this completed by Friday pretty early on. The recording will be posted both to our online Earthdata webinar catalog, which is located at the tinyurl.com Earthdata webinar. And there, the file sharing pod located in the lower right-hand corner of your screen is a persistent feature. So if you were to want to download the presentation files at a later date, you would be able to do so by accessing the recording there. I will also have it posted to our NASA Earthdata YouTube channel. We do have 65 or 66 presentations. Some of them are very short data recipe type tutorials that are posted there as well for your perusal. Any additional questions at this time?
Can I ask a question of the group?
Of course, sure.
I saw a number you said you had in the poll, a number of dark data sets. I'm hoping you're going to take the time to actually write out what they are. Were most of you aware that any digital data off tape can now be recovered, irregardless of the fact it's more than 20 years old, or even in this case 50 years old? That's a huge change. When I was, we used to always think that anything older than 20 years old the tapes were garbage after that. There'd be so much noise and so much data loss. And it turns out that's a much more durable media than we thought. As long as it doesn't disintegrate. Yeah, unfortunately, we've heard way too many cases of people saying, oh, I just threw all those tapes away. So please don't do that. There's something that can be recovered, like I say, at $35 a tape. It's well worth doing, and please feel free to contact us or the folks at Goddard on how to do that.
Okay, well, thank you, Dave. If there are no further questions, just to let everybody know what we'll do next, generally what I'll do is I will log off from the telecon portion of the webinar so you would not hear audio any longer. However, what I do like to do is leave the virtual meeting space open in the event that some of you might be interested in downloading the presentation files. So I'll usually will leave that open, and I will today an additional 10 minutes if you're interested in downloading the files, or if a question pops up, it's still being recorded, so that would be captured. And I would like to thank all of you for joining us today. Thanks very much. I'm glad you were able to attend, and perhaps we will see you online again in the future. All right, if there are no further questions at this point, we will log off from the telecon portion. Thanks very much.
Thank you.
All right, take care. Bye-bye now.